Right, this was actually a previous prelim question from a couple of years ago, and people found it quite difficult, and I think they panicked because they thought, oh, I don't know how a 3D printer works. That's not the point. Just like when you get a question and it's about like golf scores, you don't need to understand how golf works. Everything that you need is given in the description here and in the design, so you're not expected to know how the machine works. It says that a 3D printer builds up an object in layers using plastic heated to high temperature. It uses a program to control the temperature of the plastic. The user selects a print temperature and a material type using the touchscreen control panel. Different temperatures are required to melt different types of plastic. It uses sensors during the print to monitor and control the temperature. To regulate the temperature, the printer can switch heating element on or off and a cooling fan on or off. I'm just going to that because that's important for when we're looking at this design. Part of the control program shown below. So we're getting the temperature from the sensor. Is the temperature less than the user's chosen temperature? So in other words, it's too cold, so it's turning on the heating. Then it checks, is now that we've turned the heating on, is the temperature greater than the user's chosen temperature? If it's no, then, so it's not too hot, it goes and it prints it. If yes, it turns on a fan instead. And then we say, are there any more layers? And if there are, we go around and we've got a loop here. And that loop is going up and round again. Couple of things to point out here that are going to be relevant that you may or may not have spotted when you attempted the question yourself. We're getting the temperature value here, so get the reading from the sensor. And then see, right, is it less than the user's chosen temperature? That's fine. Turning on the heating, we don't then get the value from the sensor again. So you turn on the heating and you're checking the same condition, it's going to be the same value because we haven't actually updated that. It's just like if we were doing input validation and we hadn't got the user to type in and answer again. So again, like I'm saying, you don't need to understand how the machine works, but it's just looking at this design and, well, we're getting a value from a sensor here, but we're not actually updating that as we go through. State the condition used in the loop. So the condition is this. Are there more layers to print? Another construct, so we've got an if statement or condition, and we're using that to check if the temperature is less than the user's chosen temperature. If we look back at this, other constructs I could have, well, I've got an if here, I've got an if here. Let's see, if it's a conditional statement. I mean, really, this is like assignment that's going on here because we're setting something to on or off. But I think the most logical one is to get the conditional statements. When the program's tested, the design is found to be not fit for purpose as the printer frequently overheats. Two different answers for this. So explain why it might not always go down properly based on the design. It's not based on what you may or may not know about the machine. So if we look back at this design, we've already got the thing that it's not updating the sensor value. But look what happens, it turns on the heating element. See, it then goes and prints it. It goes round again. It never turns off. And if we look at the description on top of it, it says, can switch the heating element on or off, and the cooling fan on or off. So that never switches off. So the heating element's never switched off again, and the sensor value is only checked once at the start. And it's never updated, so the if statements might be using old values. So objects produced sometimes seem to be missing layers. Explain why some layers might be missing based on the design. Again, based on the design is important here. So if we look back at this flowchart, we can see where it's printing a layer now. If the temperature is right, it's printing the layer. If the temperature is not right, it turns on the fan and it skips this layer. So looks here like this is why some layers might be missing. It's turning on the fan and then it's going on and printing the next layer. And we're missing that one. And then a kind of fairly easy one at the end, the mantissa and the exponent. So 21135 is the mantissa and 3 is the exponent. So yeah, I mean, this was meant to be a more difficult program in terms of checking your logic. That was kind of the point. And that's okay. And then you'll see this when we get to the input validation. Again, it was quite a tough input validation. Like I said, this is something that you maybe haven't been assessed on yet, so I think the chances of that being in the exam are probably relatively high. That's not any kind of insider stuff, that's just common sense. So we've done some input validation with the 2022, 2023 papers, and I wanted to give you a harder input validation question again. So when the printer switched on, prompts the user to select the target temperature and the plastic type. So this is the temperature, and that's the plastic type. There are different temperature ranges depending on the material. So PLA has got to be 190 to 220. ABS is 190 to 260. So either way, the minimum is going to be 190. So we're doing input validation and we're checking that the number is greater than 190. So check it's greater than or equal to 190. The harder bit is at the other end. We're checking, well, it's a kind of hard limit. It must be less than 260, but in some cases it's going to be less. It's going to be 220. If the user chooses a temperature, it's set to range, an error message is shown. So it's an input validation. It's using a design technique, so I'm not worried about syntax here. Now you might have chosen to do this as a flowchart or a structure diagram. I've just given you a solution as pseudocode. I think it's by far the easier thing to do, and those that are going on to do higher, that's what you're going to be doing an awful lot more of. I think the chances of you ever answering the question, certainly answering the question successfully with a flowchart or structure diagram, are probably relatively low. So we'll stick with pseudocode because that's the way that you're going to be thinking anyway. So first of all, we're entering the temperature. Well, the temperature is less than 190, so it's always at least 190. Or if the temperature is greater than 260, because it's never above 260. But in some cases, if they've chosen PLA, we want it to be 220. Now there's another solution there for the condition. We could have while whatever it was, temperature, I'll just write temp for sake of space. So if the temp, so if it less than 190, or, and then we could kind of have the condition written out in full, so we could say or temp greater than 260 and material equals ABS, or temp greater than 220 and material equals PLA. That would achieve the same result. It's just a longer way of writing it out, because if it's greater than 220, that might be alright for this first one. If it's greater than 260, that's never going to be alright for either of them. So we might as well just say if it's greater than 260, regardless of what material is, it's wrong. And then showing a message and entering it again. Now again, just to emphasise, input validation, and we should know this by now, input validation is always, for you, going to be a while. Now, like I've said, occasionally there's a solution using something called an until loop, but that doesn't exist in Python, and so the way that you're always going to implement it, if you're writing a solution, is that you're going to use a while. So it's never going to be an if. And I'm maybe banging on about this a bit much, but you need to know this pattern. So it's going to be while something, an error message, and then enter it again. And that's always going to be your standard algorithm. That's not something that you're going to be able to just wing it and make up on the day of the exam. So if you're not confident that you know that and you know the steps and the kind of structure of it inside out, then that's something that you need to work on individually. And I've done input validation questions in the 2022 and 23 papers, so you can go and have a look at those. Lastly, finished programs compiled before being stored in 3D printer's memory. Describe one reason a compiler might have been used rather than any other type of translator. In other words, an interpreter. So there's multiple answers we could give here. Why would I use a compiler? We could say it only needs to be translated once, or it doesn't need the translator run every time the program is run. So if you think about this, it's on a machine, it's built into a machine that you're giving to an end user. You don't want the end user to have to run a translator program every time this is run. You also don't want the machine itself to have to say, hang on a minute, I'm just going to load the translator into memory before I do this job that I do the same every single time. If it's the same program that's running on it every time, why would you make it translate it every time when you could just translate it once and then give the translated copy to the machine, and that's what it's going to run? You might have another answer. You could also say you don't want it reverse engineered. So if it was an interpreter, you would be giving them the original source code. Effectively, you'd be giving that out to your customers, giving them the source code for your machine, which might contain sort of trade secrets that you don't want to be out there. On the other hand, if you give them a compiled one, really what you're giving them is a bunch of machine code, and it's not straightforward to turn that back into the original code. So if you give them the compiled version of the program, they won't be able to read the code that makes your machine work. For example, if you had like a rival 3D printer manufacturer wants to read the codes and say, oh, wait a minute, how does their machine work? Can we use some of their solution to make our machine better?